This is the final video in the sequence on numerical solution of equations, and in this video we're looking at the failure of the fixed point iteration method. In our earlier videos we've been looking at the solutions to the equation x cubed minus 7x minus 5 equals 0 as a vehicle for understanding how these methods work and their failure. And what we know from the change of sign method is that there are three solutions, and we found that they are within the intervals as are shown there. And in fact our further work went on using Newton-Raphson to find the actual solutions to 3 decimal places, and they're shown as well. In our last video we used the fixed point iteration method, and we used the rearrangement xn plus 1 is equal to xn cubed minus 5 all over 7. And we successfully used that with a starting value to find one of the solutions of the equation. What we're going to do now is we're going to try each of those boundaries to the intervals as a starting value, and we're going to see what happens in each case. With a starting value of minus 3, so x0 is equal to minus 3, those are the first few iterations that we would get. And you can see that the numbers are getting very large in the negative direction, and that's not converging on any of the solutions at all. Moving on then to x0 is equal to minus 2, these are the results that we get for the first few iterations. And although the convergence is quite slow, it is beginning to move towards that middle root, x is equal to minus 0.783. Similarly, for x0 is equal to minus 1, a slightly faster convergence to that middle root. And again, when x0 is equal to 0, a fairly rapid convergence upon the middle root, minus 0.783. So all three of those starting values converge on that middle root. Here are the values that you would get if you began with a starting value of 2. And once again, this converges on that middle root of minus 0.783. And the final starting value to choose is x0 is equal to 3. And although it doesn't move away very rapidly, soon the numbers get very large indeed, and like the very first value that we tried, it does not converge on any root at all. In order to begin to understand what's going on, here is a graph of the situation. We've got in red the graph of y is equal to x, and in blue y is equal to x cubed minus 5 all over 7. And the 3 places where the curve intersects the line y equals x are the positions of the 3 solutions to the original equation. With a starting value of minus 3, the diagram will look a little like that. You input minus 3 into x cubed minus 5 over 7. That gives you a new x value, which when you input it creates a staircase that is going away from the nearest solution and will not find a solution at all. Our second starting value was minus 2, and in that case when the value of minus 2 is put into the function, it gives you a new x value, which then is put into the function, a new x value, and so on. We create a staircase diagram that closes slowly on that middle solution, minus 0.783. Even though our initial value of minus 2 is very close to one of the roots, minus 2.166, in this case any starting value that is just above that value will converge on that middle solution of minus 0.783. If I choose one of our other starting values, a little way away from the actual solution, when x0 is equal to 2, I put that into the function. That in turn gives me a new value of x that goes into the function, and I have a staircase diagram that again takes me gradually back to that central solution of minus 0.783. The final starting value, x0 is equal to 3, is again exceedingly close to a solution that we know to be true, 2.949, and yet when we put that into the function, it again gives me a value of x, goes into the function, a new value of x, and again we see that it quickly diverges rather than converges onto a solution. So we've demonstrated here two aspects of failure with the fixed point iteration method. The first is that some starting values of x0, didn't converge on a solution at all. And then secondly, although we knew that there were three solutions to this particular equation, this only allowed us to find one solution. In this case, the middle solution, where x is equal to minus 0.783. We can see that starting values that were the other side of an adjacent solution led to divergent sequences. So any starting value above 2.949, the solution to the right, would diverge, and similarly any starting value that was less than minus 2.166 would also give a divergent sequence, whereas any starting value that was between those two missed solutions would eventually converge on the middle solution, minus 0.783. And it's the gradient of the g of x function, x cubed minus 5 all over 7, at those missed solutions that is of vital importance. In both cases there, the gradient of the curve at that point is greater than 1. It's steeper than the line y equals x, whereas the gradient at the middle solution that is found is less than 1. You can see from the graph that it is less steep than the line y equals x, but more on all of that later. So far we've seen that the fixed point iteration method is very quick to set up and a little less complex than Newton-Raphson because it doesn't involve the calculation of a gradient function, but nevertheless it is still prone to its own causes of failure. So we need to investigate ways that we can overcome this. And we do this by considering alternative arrangements. You'll recall that we're looking at the equation x cubed minus 7x minus 5 is equal to 0. But we can rearrange it slightly differently. If we add 7x and 5 to both sides, we would end up with x cubed is equal to 7x plus 5. And we can take the cubed root of that. So x is equal to the cubed root of 7x plus 5. And we've arrived at that format that we needed to for a fixed point iteration where x is equal to some other function of x. So we can now write that as our iterative relationship. X of n plus 1 will be equal to the cubed root of 7xn plus 5. So our first starting value, suggested by the change of sign method, was x0 is equal to minus 3. And there are the results that come from the sequence of values of x generated by this new iterative relationship. And you'll see that although it converges slowly, it does converge on the solution x is equal to minus 2.166. If we put in a starting value of minus 2, we get a slightly faster but still same convergence on that root, that solution x is equal to minus 2.166. Again, if we begin with x is equal to minus 1, we converge to that same solution, x is equal to minus 2.166. So all of these starting values, they converge on the solution x is equal to minus 2.166. The next starting value is when x0 is equal to 0. And there is the sequence of results that we get when we apply that to the iterative relationship. And here the convergence is to the solution 2.949. Similarly, when we apply x0 is equal to 2, we converge on the same root, 2.949. And when x0 is equal to 3, we similarly converge on 2.949. Let's look at that graphically. So here are the graphs. First in red of the line y is equal to x, and in blue our g of x function, the cubed root of 7x plus 5. And remember that where the curve and the line intersect are the positions of the solutions of the original equation. We remind ourselves that when we put in starting values of -3, -2 or -1, they converged on the solution x is equal to -2.166. But when the starting values were 0, 2 or 3, they converged on another solution, 2.949. When x0 is equal to -3, then the sequence looks a little like that graphically. Similarly, when x0 is equal to -1, we get a staircase diagram that converges on -2.166. But when x0 is equal to 0, the staircase goes up to that higher solution, 2.949. Although this arrangement did find two solutions, it did miss the middle solution, the one that we found before, -0.783. But we can learn something from that, because any starting value that is larger than that missed solution will converge on the upper solution, 2.949, and a starting value that is lower than the missed solution will converge this time on -2.166. And once again we can point to the reason for the failure to find that middle solution, -0.783, is because the gradient of the curve at that point is greater than 1, whereas this arrangement found the two outer solutions because in both instances there the gradient of the curve is less than 1. So far then, in trying to solve the equation x cubed minus 7x minus 5 equals 0, we've used one arrangement. Xn plus 1 is equal to xn cubed minus 5 all over 7, and we found that that only led to the finding of one of the solutions, the central one, minus 0.783. We tried an alternative arrangement. Xn plus 1 is equal to the cubed root of 7x plus 5, and that found the other two solutions, minus 2.166 and 2.949. So as far as that goes, we've used the fixed point iteration method to find all of these solutions of that particular equation. But I wanted to look at another arrangement. So beginning again with our starting equation, if we add 5 to both sides, we get x cubed minus 7x is equal to 5. And now on the left-hand side, we can take out a common factor of x, leading to x brackets x squared minus 7 is equal to 5. We can divide by x squared minus 7 to give x is equal to 5 over x squared minus 7, and we're now in the situation that we need to be for fixed point iteration, where x is equal to some other function of x, so we can turn that into an iterative relationship. Xn plus 1 is equal to 5 over x squared minus 7. And here's the graph that results from that. Again in red, the line y is equal to x, and in blue, y is equal to 5 over x squared minus 7. Once again, the intersection points of curve and line represent the positions of the solutions of that equation. I hope that you're already thinking, well, in this case there are some starting values that I can't use. Our curve has a discontinuity, and therefore we can't use either plus or minus the square root of 7 as starting values, because that would give us a 0 in the denominator and the method would fail even before it starts. You will also perhaps notice that we're not going to be able to find the solution minus 2.166, because there, as we've seen before, the gradient of the curve is greater than 1, being steeper than the line y is equal to x. I do expect to be able to find the central solution, minus 0.783, because there the gradient of the curve is less than 1, and we've seen before that it should work in that situation. But can we find that third solution with this arrangement? So let's try some values that are very close to what we know to be the solution at that point. Now remember that we can't use as a starting value the square root of 7. So I'm going to use two values. I'm going to use, first of all, x0 is equal to 3. And when we begin to put that in, we get these values coming out. And rather surprisingly, this homes in and converges on that solution, that middle solution, minus 0.783. So an alternative that we could have, which is just below the actual solution, would be 2.8. And when we put those values in, we similarly find that it eventually converges on minus 0.783. Now this is quite difficult to show graphically, and I've had to take some liberties here. But if you start at 3, you go up to the curve, across to y equals x, again up to the curve goes very high at this point, so you have to imagine this. Then it goes across to y is equal to x, down to the curve, and then across. Then it goes down to the curve, and you can see that the staircase leads to that middle solution of minus 0.783. The solution x is equal to 2.949. That third solution then can't be found using this arrangement. And we need to think about what's going on here. And we saw before that wherever the gradient was greater than 1, the solution wouldn't be found. And in this case, what we have is a gradient that is less than minus 1. In other words, is steeper than minus 1. So I've drawn onto the graph a line which is perpendicular to y equals x, so that will have a gradient of minus 1, and we can clearly see that the gradient of the curve at that point is much steeper, and that's really the reason behind its failure to find that solution using the fixed point iteration method. And so finally, to summarize, if the gradient of your curve is positive but less than 1, that would be shown by this first graph. The green curve and the red line representing y is equal to x. And I've shown the staircase diagram, broadly speaking, that would result from a starting value either just above or just below the actual solution that you're searching for. However, if your gradient is positive and is greater than 1, then the sequence of values will diverge and won't find the root. And you can see the two staircase diagrams for values starting either side of the root in that case. Then the next case is if you've got a negative gradient to your curve, and yet it's quite a shallow negative gradient, then you get one of these cobweb diagrams, where you get results just above and just below, but gradually getting closer and closer to the root of the equation. But if that negative slope is much steeper, well, then the root won't be found. You can get one of these cobweb diagrams again, but this time it's expanding, it's getting bigger and bigger and never arriving at the root that you're looking for. So when using the fixed point iteration method, prepare your arrangement and turn it into an iterative relationship, and then prepare a sketch or use a computer to draw the graphs that are the result. And you should be able to tell just by looking at the graph which root that particular arrangement is likely to be able to find. If you can't find all of your roots using one arrangement, then make an alternative arrangement, create an iterative formula, sketch or plot the graph that results, and see if that will enable you to find one of the other expected roots. Of course, once you've found a root to the desired accuracy, don't forget also to use the change of sign method for the upper and lower bounds of each suggested solution to check that there is indeed a root in that interval and you're correct to that level of accuracy.